we are going to predict the relative solubilities of the following salts. So let's start with group A. You notice in group A that there is one cation to one anion. So silver iodide, copper 1 iodide, and calcium sulfate. Even though calcium is a +2, we still have one calcium ion to one sulfate ion. We are given the individual KSP values, and we're going to look at group 1A first and compare the KSP values. And we're going to, from the KSP values, solve for the X. So let's look at each one of these. So again, we take the salt, we use the equilibrium arrows, we get a cation, we get an anion. So in this case, the KSP will equal the molarity of the cation times the molarity of the anion. So we set up our KSP expression. The KSP equals X times X, where X is the solubility. So for silver iodide, we're given a KSP value. We equal that to X squared. We solve for X, and we get this value for X for the silver iodide. For the copper iodide, we are given a KSP value. We equal it to X squared. We solve for X. We get this value for the X. Our copper sulfate also fits into this category. We're given the KSP for the copper sulfate. We equal that to X squared, and we solve for X. So then, once we have our values of X, we will just compare the X values. So if you look at the exponents, usually you can rely on the exponents. So this is 10 to the minus 3. This is 10 to the minus 6. This is 10 to the minus 8. So the most soluble would be the 10 to the minus 3. That was our copper sulfate. We put that first. And then 10 to the minus 6, that's our copper iodide. And then 10 to the minus 8, that's our silver iodide. So we just put the values in order, and that's how we get the most soluble as the copper sulfate. So calcium sulfate is more soluble than copper 1 iodide, is more soluble than silver iodide. So let's look at another example. Now, this case is our group B. And so we're going to have to, again, set up the equation here, the reaction. So this is our copper 2 sulfide. It breaks up into copper ion and sulfide. The KSP would be equal to X squared. So you figure this is X and this is X. We are given the KSP value. We equal that to X squared, and we solve for X. So this is our X for the copper 2 sulfide. So let's do the next one. So the next one is the silver sulfide in equilibrium with 2 silver ions and 1 sulfide. So this would be a 2x, this would be x. So we want to take our 2x, put it inside our parentheses. We want to take our x, put it inside the parentheses. And then because we have the 2 in front of the silver, we would want to use the exponent 2 for our KSP expression. So we end up, when we do the math, getting 4x cubed. So we take our value of KSP, we equal it to the 4x cubed. We solve for x, and so this is our x for our silver sulfide. So now we have the bismuth sulfide in equilibrium with 2 bismuth, because there's 2 in our formula, 3 sulfide because there's 3 in our formula. So we're going to have 2x and 3x. So we're going to take our 2x, that will go inside our brackets. Our 3x will go inside our brackets. And then remember, because we have 2 in our balanced equation, our exponent is 2. We have 3 in our balanced equation, so our exponent is 3. So we set up our KSP expression. It's equal to the value that was given for us. So this was the value of the KSP. This is when we put inside our parentheses our 2x from here. So this 2x went inside our parentheses here. This 3x went inside our parentheses here. And then because we had 2 in the balanced equation, that was our exponent here. Because we had 3 in our balanced equation, that was our exponent here. So when we simplify, we would have 2 times 2 from here. We would have 3 times 3 times 3. That would give us 108. And then the x squared times the x cubed will give us x to the power of 5. So the math would be to take the value of the KSP and equal it to 105x. So when we do that, we get this expression when we isolate for x. And then when I divide the 1.1 times 10 to the minus 73 by 108, I get 1.0185 times 10 to the minus 75 equals x to the power of 5. So you should have on your calculator a button that looks like this. You should be able to find this button and then solve for x. So then once you have your x values, you compare them. So in this problem, the most soluble was the bismuth sulfide. That was more soluble than the silver sulfide, was more soluble than the copper sulfide. So let's look at another problem. The question is asking, what is the solubility of silver chromate given the KSP value of the silver chromate, and it's in a 0.100 molar solution of silver nitrate. Now remember, nitrate is a spectator ion, so we can just completely ignore the nitrate. But we do have some silver ion from the silver nitrate solution. So we need to take that value and put it in initially for the silver. Initially, we have 0 of the chromate. So remember, for initial, we have some initially from the silver nitrate, and we have 0 chromate. When we take the formula and break it up, we will have to remember that there's a 2 here in the formula, and so that gives us the 2 for the silver. So again, remember to put in your plus here. This is going to be, that minus should be up here with the 2. So now that we have the balanced equation, we can use it. And once again, we're going to ignore the column for the silver chromate. Because there's a 2 here, we gain 2x, so plus 2x, plus x. And then we just have to follow down from our initial and our change to determine the equilibrium. So this is a 0.100 plus 2x, and the chromate is an x. So once we have the equilibrium row, we're going to take this and put it inside the brackets for our KSP expression. And then this is just going to be x inside the bracket for our chromate. So we set up our KSP expression based on the balanced equation. We were given the value of the KSP. So we put the value of the KSP here. We put it equal to our equilibrium row, tells us what to do here. So this was the equilibrium for the silver. We put it in here. And then this was the X for the chromate. We put it in here. And then what we're going to do to simplify is we are going to assume that this X is small. so we won't even use it. So that means that we can approximate that the value of the KSP equals 0.100 squared times x. So we solve for x, and the x is what the question was asking for. The question was asking for solubility, and this is what we got. So that's our answer.